let me start with chapter 8 right now with a review of what I was discussing last week. So, in essence, chapter 7 is about chemical amounts, not chemical equations. So when we were looking at chapter 7, the highlights of chapter 7 would be Avogadro's number. That's a main topic of that chapter. The idea of the mole, but also the idea of molar mass. And then we also did some conversions from these three entities. So we went from amount in moles to number of particles, which is what Avogadro's number gives you, and then to grams, which is what you can weigh in a laboratory. When you use a scale and you need to weigh a chemical, you need to use grams. So in a way, we went from grams to mole to particles or items. And that's really the bulk of the chapter. But in the context of that material, I introduced chapter 8 material. I introduced the idea of chemical reactions and chemical equations. That's probably where the confusion arises, that I was covering already chapter 8 stuff.
Yeah, so I have gone through the reading and I'm up to oxidation and reduction.
Okay.
And I thought that may have been covered on Thursday when I was absent.
No, I did not, but that's a great topic to cover in the remaining of the semester. So we may get to oxidation reduction today, we may not. But we're going to take a formal look at the different kinds of chemical reactions that you should be able to recognize. So that's a good point. Once again, the summary of chapter 7, in addition to this, is that you should be able to look at a chemical equation, a simple one. We only looked at hydrocarbon equations and balance it. But that's also chapter 8. So we're going to do more balancing of equations. We're going to be working both in moles and in grams in this chapter. But let's just talk about what is a chemical reaction, which is the beginning of chapter 8. So with this in mind, when one type of chemical becomes a different type of chemical, we use this process, and I'm going to use letters right now, although we have seen chemical reactions and equations before. Let me just make some observations about the generic nature of these reactions. So you can have two chemicals converting to two other chemicals. They look similar, but they're different. So A may look a little bit like C, but it's different than C. And I'll give you some examples soon. Just like B may look like D a little bit, but it's different. It has different properties, different boiling point, different color. Everything is different about them. Now, in every chemical reaction, you have an arrow. That arrow is important because it tells you where the reaction starts and where the reaction ends. The starting of the reaction is called the reactants. The chemicals that are interacting with one another to do something, to become something. And then on the right side of and I shouldn't say the right side, but on the other side of the arrowhead is the products. Why did I correct myself? Well, because I want you to critically think about what I'm going to do next. This diagram which shows this arrow pointing in this direction. The arrowhead is pointing in that direction. Shows you the reactants before the arrowhead, the products after. In other areas of chemistry, sometimes you have what are called reversible reactions. Reactions that can go in one direction, but they can also go in the opposite direction. So if I were to change the arrowhead here, then you have to understand that these names are changed too. These are no longer the products. These are now the reactants. And these are now the products, not the reactants. So you look at the arrowhead, not necessarily left and right. Does that make sense? Be careful, because once again, if I want to be correct about that, I need to actually write down that these are the products and these are the reactants because of that arrowhead pointing in that direction. Okay? So always look at the arrowhead. Now, 99% of the time, certainly in this course, we're going to have it the other way around, with the arrowhead pointing to the right. And that's why sometimes I catch myself saying the products are on the right side of the equation, because that's the way we write it most of the time. Just be aware of that fact. Now, in a generic chemical equation like this, again, let me put back the labels. We need to indicate more information. We need to provide more information as to what is happening. That extra information comes in the form of the state of matter for every chemical involved. And there are 5 states of matter that you should indicate. They are indicated in a lowercase letter, and they are placed in a parenthesis, and there's 4 of them. So G stands for gas, L stands for liquid, the state of matter liquid, S for solid, and AQ is a special case of a state of matter known as aqueous, meaning in water. Some substances are never found in a chemical reaction in their pure state. They are found mixed with water, which is often referred to as dissolved in water. But water is not really reacting, it's just the vehicle, the vessel in which the reaction is taking place. So in this particular generic form, I could have A as a gas, B as a solid, C as a liquid, it's just an example, and maybe D as an aqueous solution. The point is that you have to indicate those states of matter. They need to be written. Now, sometimes you may see a symbol like a triangle, and that symbol means that heat is needed for the reaction to proceed. And that triangle is often placed on top of the arrow. And that just means needs to be heated. There may be other symbols that you encounter in other more complex reactions, but these are the basic ones, the generic ones that we're going to look at. Now, in that hypothetical reaction that you see there, let me see if I can get to the part that describes that. Well, of course, I didn't mention these plus signs, but those plus signs means combining or combination, this and that. This and this, that and that, that's all what that symbol is indicating. Now, not necessarily in every reaction, but in some reactions, you may have a number in front of the symbol for the chemicals that are involved. Those numbers, which I'm not showing here, but I'm showing you the location, are known as coefficients. And coefficients just tell you the number of items involved from every particular chemical. So these boxes may have a value of 1, which we don't write, or they could be 2, 3, 10, always whole numbers, always integers. Again, if they are ones, we don't write them. If they're 2 or any other integer, then we need to indicate them there. And they're just simply known as coefficients. Now, we looked at this reaction before. Well, similar to that reaction. This is actually the production of water. But let me jump ahead because we already saw some of these ideas of balancing equations. And I need to show you the different kinds of chemical reactions that you may encounter. So we already did a lot of this balancing. So we're way ahead. Here is where I wanted to be. Today we're going to finish these theoretical aspects of Chapter 8, and then we're going to start looking at some problems with real numbers, real balancing equations like from your homework. When you have a transformation going on, when you have two chemicals combining to form two chemicals, or when you have one chemical breaking apart to form two chemicals, you have different kinds of chemical reactions. So let me see how well this part of the book explains these things so that I don't have to write on the board and we can actually make sense of them. I will be listing them in the order they appear here. So we're going to deal now with the types of chemical reactions that you should be able to recognize. So when you look at chemicals, you should be able to tell which type we are dealing with. So the first one that we're going to look at is called a combination reaction. What happens in a combination reaction? In this example, you have two reactants before the arrow. This is before the chemical reaction takes place. And you have only one product as the end of the reaction. You see that? You start with 2, you end with 1. I could write this generically as A plus B yields AB. So A and B combined. That's why it's called a combination. In this example, they actually show you sulfur is combining chemically with oxygen to form a completely new chemical called sulfur dioxide. This guy is different from those two. Different properties, different entity. The states of matter are indicated. As I mentioned last week, oxygen, when present in these chemical reactions by itself, when it's alone, always is going to be present as a bimolecular or dimolecular entity, O2. On the same category, you have hydrogen. Hydrogen is always H2, and nitrogen. Nitrogen is always N2 when found by itself. When it's found combined, this happens to be SO2, but you could have SO3. It's only when they are individually found in the reaction. So again, you start with two individuals which combine to form one single unit. Keep in mind, everyone, that we have the formation of bonds, the breaking of chemical bonds. So we are adding glue, we're removing glue, we're regluing, if you will. So we may break some bonds and form new bonds. We make, in this case, join two different entities with one bond to form a new product. That is always happening, the formation and the breaking of chemical bonds. Whether they are covalent or ionic is still the same. Now, here's a little example, and I say little because it's in tiny characters. Let me make it a little bit bigger. Of another combination reaction. Here you have actually magnesium combining with oxygen to produce magnesium oxide. But in this example, you actually see coefficients. You see a 2 in front of the Mg. That has nothing to do with the chemical formula. It just tells you that two of these particles, so if I were to repeat that chemical reaction, 2Mg combines with 1 O2 to produce 2Mg. And last week I emphasized that we are not creating or destroying matter, we're transforming it. We're combining these two to form a new chemical, but it's a new chemical coming from all chemicals that are already there. Now, if you count units of every single element involved, as we did last week, we're going to find out that this is a balanced chemical equation. It has the right amount of magnesium on one side and the right amount of magnesium on the other side. Same thing for oxygen. So we did introduce that topic, which is actually the bulk of chapter 8. So we're ahead. Now we're going to do some balancing ourselves, but suffice to say that this chemical equation as written, the only thing is missing is the states of matter, which you see there. Anytime you combine two different entities to form one is a combination reaction. So that's type 1. Let's take a look at a different type of a chemical reaction. And we're going to look at a decomposition reaction. Now, in a decomposition reaction, the opposite that we saw on the first type is taking place. Now you are breaking apart a bigger entity, a bigger molecule, into two smaller components, all three different from each other. So in the generic form, using these same symbols, you have A and B separating into A plus B. And in the example that you see here, if you carefully look at this formula, HGO, HGO has Hg, which is mercury, and it has oxygen, but they're chemically combined into some form of a mercury oxide. When these break apart and become two different entities, mercury alone and oxygen alone, we have a decomposition of the mercury oxide. It just fell apart. Perfectly fine. Now, these reactions require heat. There was an addition of heat needed. Some other examples. Let's take a look. The decomposition of calcium carbonate. And again, it's a little small. You still have those pens, huh, Carol? They don't work. No, just kidding. I mean, as syringes. They do work as pens. I've been using mine. Okay. So here you have another example of a decomposition. Calcium carbonate Difficult to see the components, but this has calcium, has carbon, and has oxygen. It's becoming two different chemicals, very different from the original one, calcium oxide and carbon dioxide. This is one of those difficult ones to predict, but it is what it is. You see the result of the decomposition right here. This has to be heated. From one substance that happens to be in the solid state, you get two substances, one solid, one gas. Completely different composition, completely different properties for all three of them. Please start thinking, how am I going to identify these guys when I look at them without a guide? Well, it's not that difficult. You just count particles and take a good educated guess. I'll show you some examples very soon. Now here, we're going to talk about two different kinds of what are known generically as replacement reactions. So I'm going to separate them into the two that we're going to encounter. One is called a single replacement reaction. In a single replacement, and here we have a new symbol in the form of a letter C. We have A combining with a chemical BC, generically speaking, and C forms a new partnership with A, displacing B. So that displacement means a replacement. It's almost like when A encounters this couple, the couple of B and C likes A better than B. So, sorry for saying it, but he divorces B and he marries A. That's what is happening. It's a single displacement of A, which we call replacement, in which B is left alone, and C becomes a partner with A. Horrible example, but an example that I think unfortunately works and sometimes happens in real life, right? This is observed quite a bit in metals, in ionic compounds. So what is the example that the book has for that? Let me scroll down. It's going to be one metal being replaced by another. And here, hydrogen is showing up as a metal. Remember, hydrogen is unique. Hydrogen can be metal or non-metal. Here is combined with chlorine to form hydrochloric acid. So hydrogen and chlorine have a partnership. We call that hydrochloric acid. However, that partnership is not very good, and when zinc, a metal, comes into the scene, into this situation, into this chemical reaction, it kicks out hydrogen. It basically says, move away, I want to partner with chlorine, and now you are on your own. So hydrogen becomes a single element there by itself. Zinc replaces the hydrogen and now is in partnership with the chlorine. If you see that, you have a single replacement. But it's in fact displacing hydrogen from the partnership. And here you see solid, aqueous, gas, and again aqueous. This actually gives you an idea of what is known as the chemical reactivity of the metal. So zinc is said to be more active than hydrogen, and that's why it's kicking it out. We can actually classify different metals for that type of reactivity. Some are more active than others. Now let's take a look at another example. And hopefully you can identify what is going on. Now this one is a little different. but it's still involving displacement. In this case, the displaced substance is not a metal, but it's a nonmetal. Excuse me, chlorine. Chlorine is going to kick out bromine of this partnership and replace it. So now instead of having potassium associated with bromine, we have potassium associated with chlorine. But I hope you can follow along and see how that guy is being displaced or replaced by the chlorine, and now it shows up by itself. If you pay attention, it's not that hard to distinguish them. Now, this one is a little bit more tricky, and this is number 4. It's another type of replacement reaction, but it's known as double replacement. Here you have actually 2 partnerships going on. It's like 2 couples. These couples are exchanging partners. They got bored. I mean, bad examples that I'm using today, but in essence, A and B are in a relationship, C and D are in a different relationship. A likes D better, B likes C better, so they rearrange, and now they have this different partnership. That's what's going on. So A partners with D now, which was the partner of C, and B partners with C, which was the partner of D before. You're going to see that the first one is typically a positively charged ion, and the second one is typically a negatively charged ion. So A can only partner with a negatively charged ion, so it's going to partner with D. And B, being negative, is going to partner with C, which is positive. That's why they are flipped in the order here. C appears first because it's probably going to be positively charged. So these are metal, non-metal, metal, non-metal. The activity of the metals is going to be what drives this reaction to take place. But your question is very valid. I mean, why is it that happens? Well, because when this is isolated by itself, it's happy, but when it encounters this chemical, it likes D better than B. And the same happens to C. C decides, you know what, I'm more stable, more happy with B, so I'm going to form a different partnership. That's what's going on. Now, is it predictable? That's not going to be your job in this course. So we're not going to be able to predict all the time what's going to happen. But if you look at in other words, I'm not going to give you a problem without telling you, okay, so this is a double replacement reaction. What you need to do is predict how this guy, barium, is going to replace sodium to form a partnership with sulfate, giving you barium sulfate. And sodium is going to be replaced by barium, so it's going to have to partner with chlorine to form sodium chloride. I mean, if you look carefully, take a deep breath and you look, you can see the trading places, if you will. Keeping in mind that you have to be able to recognize metal from non-metal. So the metals are always listed first. Barium is a metal, sodium is a metal. In the product side, they're still listed first. So these are going to be positively charged, positively charged. The second member of this partnership is always going to be negatively charged, negatively charged. And they remain first and second, first and second. Okay? So in this scenario, we have, to begin with, A partner with B, C partner with D. When the double replacement takes place, I need to keep A as the first element. I'm going to put D as the second one. And then C has to stay as the first one, and B as the second one. They need to be in the same location. And that's what you see over here. Well, I did it, you know, in a not with the color coding that you see here, but that's the outcome that you see. When we start practicing some of these predictions of the type of reactions, I think you're going to get confidence. So we have only one left, which we have already looked at. These all four are new. We never talked about this before. Number 5, we spent almost the entire week last week talking about it. So if you want to guess, and you guessed combustion, you got it right. These reactions should be familiar to you. So the number 5 is called a combustion. And it is perhaps the easiest to recognize because it's always going to have oxygen as one of the reactants, and it's always going to have carbon dioxide and water as the products. So we saw that last week. That's the last type of chemical equation that we will see. That one, I don't use A and B's because it's not possible. In this one, you have always a chemical. Well, I guess I can say A combines with O2 to produce carbon dioxide and water. It doesn't tell me what A is, but A is going to be always a hydrocarbon, a fuel that can be burned. So a combustion implies burning, and it's always going to require heat. And it generates actually energy. So you may sometimes see the word energy written as a product because it releases heat. Okay? Now these are your 5 type of chemical reactions that you should be able to recognize when you look at an example. Let me just make sure that everything has been covered here. Then I'll go back and we'll do some problems. There's plenty of problems to do. We do have the oxidation reduction reactions left, which is a really interesting topic. So I'm going to leave that either for the end of today or for Thursday, because this is a huge concept that actually can be overwhelming, but once you know how things happen, you will know how to predict them. So we're going to proceed in order. And of course, we're going to start really very simple here. One of the questions, and remember, I don't ask you to memorize things, but I think these are intuitive. So which of the following chemical symbols is used to designate that a chemical is in the gas state? Just remember the first letter. So not a big deal there to remember. Even though no memorization is required, I think you can easily see that should be the answer. Now, this is about balancing. But it's not asking you to write the balance equation here. It's just asking you to balance it and then express the number of particles of nitrogen only, so that's kind of misleading for, it's oxygen, you're right, it's oxygen. State the number of atoms of oxygen in the reactants and in the products for each of the following equations. So it's basically telling us we need to learn how to count atoms by looking at formulas. The N stands for Avogadro's number, if you will. This equation is already balanced. So, because it's balanced, the amount of oxygen on one side is going to be exactly the same as the other side. So it's asking you for a single number, which should be the same for both sides. So we don't need a comma, we don't need 2 numbers, we just need one number of the total oxygen on either side.
Is that
Yeah.
were right.
You're out. My apologies for that. I'm so sorry for all of that struggle, but that finally I figured out. Okay, so 3 times 2 oxygens is 6. 1 oxygen times 1 is 1. 6 plus 1, we should write 7 here. And this should come as second nature to you. So just to prove that we are right, we're going to put just the integer and submit. So let's do the same for this one. This time they want also oxygen, right? The number of oxygens. It should be balanced. Let's count. 2 times 2, 4. 4 times 1, 4. It is balanced. So the answer, on either side, there are 4 oxygens. So that should be your answer. Let's go to part C without answering that one. How about here? How much oxygen is in there? Well, let's take a look at the balancing of the oxygen. There's no oxygen on the first reactant. There's oxygen here. 5 times 2 is 10. So there's 10 total on the reactant side. Over here, there's oxygen on both products. We have 4 times 2, 8 oxygens. 2 times 1, 2 plus the 8 is 10. So it is balanced, and the answer should be 10. Now, let me go back to the top, because I want to take advantage of this. And let's take a look at this equation. We're going to answer a different question. Looking at the 5 types of reactions that you see on the board, what type of reaction is this? What type of reaction is this? Choosing from these 5. So let's take a look. In the reactant side here, we have 2 different chemicals, right? So the answer cannot be that, but it can be that because there's 2 different chemicals, right? It cannot be, well, yeah, it can be that one and it can be that one. The only one that we have eliminated is that, plus the combustion because it's not a hydrocarbon and there's no oxygen. So we have 3 choices to pick from. Is it this one? Well, on the right side, that's the one we eliminated. Is it this one? Well, on the right side, there's only 1 chemical in combination. Here are 2 chemicals. So it cannot be a combination, right? In combination, you have 2, you end up with 1. So it cannot be that. We got rid of that, we got rid of that. Now let's take a look at the single replacement. You start with 2 different chemicals and you end up with 2 different chemicals. So it could be that. But it could be this one too. This one is out. So is it a single replacement or is it a double replacement? Well, look at the 2 chemicals. This has nitrogen and oxygen. It's not a single entity that is actually being decomposing, changing, if you will, into something else. This is also a 2-member molecule, hydrogen and oxygen, which is becoming something very different. So you should be guessing. I'm not telling you that it's not even a question in the homework, but you should be guessing that this is a double replacement reaction. If you were still hesitating, just look at how the partnerships became, in fact, new partnerships. That looks nothing like that. Well, a little bit, but really NO2 versus NO, they're different. So there's already something happening there. Now, what about the next one? Is the next one type? What type of those 5? So once again, we look at the left side, and we have only 1 chemical here and 1 chemical there. So we're starting with 2, which it cannot be that, but it could be that, right? That one is out. This one could be it. This one could be it. This one is out because there's no oxygen alone. So which of the 3 remaining is this? What's happening? This is a single element. It looks more like this than like that or like that. This has two partners. Two partners, two partners. This is only a single element. So it cannot be decomposition, it cannot be double replacement. We are left only with single replacement, and that's most likely what it is. The carbon is replacing the oxygen to form CS2. All bets are off when there's no answer, because I'm not going to tell you, oh, I'm 100% sure that this is a single replacement. But that's what it looks like, and that's what you had to go with. Now this one, I'm going to let you answer because we've seen this before. So what do you see on the left? You see oxygen by itself. I mean, of course, you see oxygen in this example, but not in the generic one. In the generic one, here you see oxygen by itself. On the product side, here you don't see water. Here you don't see carbon dioxide. Here you see water, and you see carbon dioxide. There is water, and there is carbon dioxide. So oxygen as a reactant, CO2 and H2O as products, this always means combustion, right? That wasn't the question, but I wanted to take advantage of that to show you how you can actually make those guesses. Okay, so let's go back to answering the question about oxygen here. How many oxygens are on the left side? Total. On this one, part D. Total oxygens on the reactant side. Oxygens.
4.
So 2 times 2, 4. How many oxygens are on the right? On the product side. 4 times 1, 4. So it is balanced, and the answer is going to be 4. There are 4 oxygens on both the reactant and the product side. Okay, next type of question. So now we want to separate the total number of each individual atom on each side of the equation. So this tells me that this is a balanced equation because they're not distinguishing whether they want the reactant or the product side. But let's balance it. Let's count and make sure that it's balanced. How many carbons are in the reactant side here? How many carbons do you see? 1, right? Everybody. On the product side, how many carbons do you see? 1. So the carbon is balanced. We did that last week a number of times. How many hydrogens do you see on the left? Total 4. How many do we see on the right? 2 times 2, 4. Balanced. How many oxygens do we see on the left? 4. 2 times 2 is 4 oxygens. Correct. How many do we see on the product side? 4. 2 plus 2 times 1 is 2 plus 2, 4. So we have 1 carbon, 4 hydrogens, 4 oxygens. And that's what the answer should be. They want it separated by commas. So 1, 4, 4. Let's count again before I submit it. 1 carbon, 4 hydrogens. That's the second one. 2 times 2, 4 oxygens. That's the answer. If your equation looks different, just make sure you answer the question for your equation. Okay, how about this one? So we have phosphorus and oxygen only. We already know that these are all balanced. So there should be the same number of phosphorus on the left as on the right. And they are indeed. How many phosphorus? 4 and 4. How many total oxygens on the left? 5 times 2, 10. On the product side, 10. So 4 and 10 is the answer. Okay? I put a period, comma 10. Oops. Okay. Now, once again, before I move on, can you tell me what type of reaction is this of those 5 kinds?
Looks like combustion.
So you think it looks like?
Oh, no, there's no catalyst, sorry.
Right.
Combination?
Looks like a combination. You start with 2 different ones, yielding one combination of the 2, yielding one combination of the 2. So it's most likely a combination reaction. It doesn't look like anything else except combustion because it has oxygen, but there's no carbon dioxide and water on the right. If there's no carbon dioxide and water on the product side, it cannot be a combustion. So it is most likely a combination. Okay, so let's go to the next type of question. Now this is more straightforward. We just need to know if they are balanced as written or not. So as we did last week, we're going to count elements of each kind, bundle them together, and determine whether or not this is balanced. So how many sulfurs on the reactant side as written? How many S's do you see? 1. I mean, don't count the solid state. 1 S, and how many on the right, on the product? 1. Also 1. So the sulfur is balanced. Check. How many oxygens do we have in the reactant side? Total. 2 oxygens on the reactant side. How many on the product side? 3. So it's not balanced. And that's what you had to answer. So the answer, of course, is not balanced. Let's take a look at the next equation and glancing at it, let's see if it's balanced or not. I'll let you do that one. See what happens. Is that balanced? How many magnesium do you see on the reactant side? Grand total of magnesium. Only 1, right? There's no more magnesium. There's a 1 in front, implicit. How many magnesiums do you see on this side? Mg3, so there's 3 magnesiums. So it's not balanced. We don't even have to look at the nitrogen. Not balanced. Now, how do we balance it? I mean, I know we have plenty of opportunity to be balancing equations, but I want you to really feel confident about balancing. If I have 3 here of magnesium and only 1 here, what can I do to this coefficient? Put a 3, a big 3 in front of it. Remember, that doesn't change the formula. It just changes the amount of magnesium. So a 3 there will balance the magnesium. Now the nitrogen is already balanced, and we didn't add anything to here, so that's going to remain balanced. So just a 3 right there balances the whole thing. That one wasn't that complicated. We didn't need too much of a trial and error. How about this one? Is it balanced? PCl3, Cl2. So let's count phosphorus, P. How many P's total on the left? There's only 1. So I hear balance. Yes. So 1 phosphorus, 1 phosphorus. We have 3 chlorines and 2 more. 5. 5 on the product side. So yes, I did hear balance, so you are right. And just to complete it, let's do this one because oxygen is in a different location that normally is found, meaning in between other elements. So is this one balanced or not? Let's count carbon. Before the arrow, how many carbons? How many C's? 1. After the arrow, product side, how many carbons? Only 1. This 3 doesn't apply to the carbon. The carbon still has a 1 there. So the carbon is balanced. How many oxygens on the left? There's only 1 there. How many oxygens on the right? Only 1. So that's balanced. How many hydrogens on the left, on the reactant? 2 times 2, 4. How many on the product side? 3 plus 1, 4. So that's balanced, right? Okay. So let's do one more, and then let me just remind you that today we don't have a lab meeting because we're not ready for the stoichiometry lab. We will be ready next Tuesday. However, I'm going to move to the lab, and if any of you want to ask questions or need more help, I'll be there, to answer any questions. So let's do one more problem, and then we can call it quits. I have 3 minutes left here. Okay, we already did something like that, so we're going to skip that. Now here are the classifications. So let's classify some of these. That way I take advantage of this writing here. So what is this type of reaction? What's going on? Ignore the coefficients. We're only looking at the number of particles. So from 1 and 2 different chemicals, we're getting only 1 chemical. From 2, we're getting 1. Which one looks like that? In fact, let me erase all of these. Yes, I agree with that. Looks like a combination, right? We are doing that, 2 chemicals, producing 1 chemical, only 1 chemical. So I agree, it's a combination. I don't even have to look at the others. It's definitely not a combustion because there's no carbon dioxide and water. Right. Okay, so we got it right. Let's take a look at the problem. I know I said only one more, but okay, I think I'm going to leave this one for next because it's going to require a little bit more thinking. But we're going to pick it up right here with question 5 of the homework.